Now, let's do the hard one. We'll do the hard one. So, what we have this time is we have a point. We just call it point P because we have no imagination. And then we have a line. Now let's make something clear here. We'll just call that line L. How many lines go through point P and are perpendicular to line L? One. Good. How many lines go through point P and are parallel to line L? Only one. Okay. So this time we're going to find the one that's parallel, and we're gonna actually construct it. We're going to construct it by, remember, making the corresponding angles congruent. Because if two lines are cut by a transversal and the corresponding angles are congruent, then the two lines have to be parallel, don't they? So what we're going to do is we're going to draw the transversal first. So I guess I'll label that one T for transversal. And now this angle right here, what I want to do is I want to copy it right up here so that the corresponding angles are congruent, and then the two lines will have to be parallel. So here's how we do it. I'm going to do this part in red so you can see what's going on. Put my compass right here. Now I can adjust however I want, doesn't matter. Okay, just kind of get it out here a ways. And I'm just going to kind of go like this, about like that much, and I'm going to make an arc. You with me? Pretty simple. Now, don't adjust the compass. Come up to point P, make that same arc. I got to make my line, my transversal, a little bit longer. Okay, have you caught up? Take your compass now. What we're going to do is we're going to kind of measure this little distance right here. So we're going to put our compass on that intersection, and we're going to adjust it so that it's on the other intersection, like that. See this? So it looks like this. Now don't mess with your compass. Come back up here to the other one. Put it on the upper intersection and make that arc again. So we're coming here. We're figuring out what that arc is to hit the intersection, and then we're coming up here and we're doing the exact same thing right there. What we've actually done is created two congruent triangles. We're going to talk more about congruent triangles later, but if we look at the distance from here to here and from here to here, that's the same. We made that the same. From here to here and from point P up to here, those two are the same distance, equidistant. And then we just made from here to here and from here to here congruent. So we made all three sides of two triangles the same measure. And we'll talk about why that makes a big difference later. But now we just come in here. Now these two lines should be parallel because these two angles should have the same measure. So our two lines should be parallel. So there's the line that goes through point P and is parallel to line L. Thought maybe if you have these in your notes, you can keep that paper and then you can kind of see what you did in what order. Maybe it'll bring back some memories when you have to, I don't know. Do it on the quiz tomorrow? Just watch. Don't do it again, just watch again, okay? segment, endpoint, endpoint. We'll call it XY. Just watching. I want to find the midpoint. So, more than halfway. See, I'm more than halfway. Make a big arc. Come over here. Same hole. I haven't moved this thing around at all. So I'm making that same arc. Now, if I go from here to there, what do we know about that point right there? Good job, midpoint. What do we know if we actually draw this line in? What is that line called? Perpendicular bisector. Because it goes through the midpoint, it's a bisector, and it will be perpendicular to the segment. Okay? Now, if I have a line and a point that's not on the line, how many lines go through point P and are perpendicular to line L? Only one. Okay, we're going to find it. Remember? So in this case, point P is up above, so I just adjust my compass somewhere, doesn't matter where, but I need to be able to make this smiley face in this case. Right? And then from these two intersections, I'm going to make arcs from there. Now these two arcs, they don't have to be the same as the original, but they have to be the same as each other. So from here, okay, let me do this one in red so you can see the different one. I'm just going to make that arc, and then I'm going to come over here, and I'm going to make the same arc like that. Now, when I draw the line through point P through this intersection, this line goes through point P, and it is perpendicular to line L. So it's the perpendicular bisector. It's not just a bisector. Remember, a bisector just goes through the midpoint of this segment right here. Line doesn't have a midpoint, but it's the perpendicular bisector. So we have a right angle right there. Okay? All right, so you got your notes. You should all be able to get perfect score on that quiz tomorrow. No problem. So, let's look at a coordinate plane for a minute. We've been talking about this, but let's say I have a line. Well, that's not going to work very well. There we go. Let's say I have this line, and it's going down 2 over 3. Down 2 over 3. And, of course, it's going to continue that process all the way down through here, isn't it? So what does it slope? What? Say it one more time. What is it? Oh, negative. Negative. Negative 2/3. That's correct. Negative 2/3. I wasn't hearing the negative. What can you tell me about every single line that's parallel to this line? Its slope is negative 2/3. So can I start at any point on the graph, go down 2 over 3, down 2 over 3, and that line is going to be parallel to this one? So I can start here, and if I go down 2 over 3, down 2 over 3, if I draw that line in, it's going to be parallel to our original line? Okay. What about perpendicular? So this one's parallel. What about a perpendicular line? Okay, its slope would be 3/2. How do we describe what? So, are they reciprocals? Remember how we said it? Opposite reciprocals. So reciprocals, they have the same sign. The reciprocal of negative 2/3 is negative 3 over 2. So if they're going to be perpendicular, they're not just reciprocals, they're opposite reciprocals. Got it? So if we start at some point here, if we go up 3 over 2, up 3 over 2, up 3 over 2, up 3 over 2, then we get a line that not only bisects it, but it's actually perpendicular. Now, what do you think about all those lines? Yeah? Are they all parallel? They're all parallel, aren't they? I've written them a little bit differently, but they're all parallel. Still parallel? Now this one's in standard form. It's not in slope-intercept form, is it? What about that one? What form is this one in? What is it? Point slope form. That's right. Okay. And there's our slope right there, isn't it? So, all right, we can see that those are. And then, of course, the perpendicular, I hope you can get those as well. Let's see, 2/3. Well, if we want it to be perpendicular to these lines, I guess it would have to be -2 over 1, wouldn't it? -2 over 1x, y equals 7 minus 2x, something like that, so that the slope was the opposite and the reciprocal. Turn to page 150. There are 3 theorems we need to talk about today. The first one's called the linear pair perpendicular theorem. Sounds awful, doesn't it? Linear pair perpendicular theorem. So here's what it says. If I have a line H here, and I have another line G that intersects H, and I have a couple angles, angle 1 and angle 2. What do you think about this? Angle 1 and angle 2 are congruent. If you know they're both congruent, where does that lead you to? What does that make you think? The 2 lines are perpendicular? Can we do something in between that? Is there something that you think in between, oh, they're congruent, so the 2 lines are perpendicular? So they both add up to 180, and they're congruent. They're right angles. They both have to be right angles, don't they? Or can we even back up one more step? Their measures have to be 90 degrees. So that they add up to 180 and they can be congruent. You all okay with that? Okay. And if their measures are 90 degrees, they're right angles, and so G and H are perpendicular. So that's what the theorem says. The linear pair perpendicular theorem says if 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. A linear pair of congruent angles. That's a lot of words. That's a lot of vocabulary, isn't it? You didn't know any of that vocabulary a couple weeks ago. Linear pair, you get that now, right? Of congruent, you know what congruent means? Of congruent angles. So there you go. I don't think I'd have to teach you that for you to figure that one out, though, would I? If I gave you this problem and said angle 1 is congruent to angle 2 before we even talked about it, and then said, what do you think about line G and line H? How many think would you have thought, oh, they got to be perpendicular? Especially since we were just talking about perpendicular lines, right? Probably figure that one out yourself. Okay. The next one is the perpendicular transversal theorem. Oh. So I've got these two lines. Are they parallel or not? Why not, Chase?
Can't just assume they're parallel, right?
Yeah, are the arrows on the ends?
Yeah.
So is there any indication to tell you that they're parallel other than they look like it? Okay, so we don't know if they really are or not, but they sure look like it, right? But we don't know if they are or not. However, if there's a transversal, if line T is perpendicular to line L and line T is perpendicular to line M, are line L and M parallel? They are, aren't they? So if it's perpendicular to both of them, what does perpendicular mean? It means we get what type of angle? Right angles. And what do we know about all right angles? They're congruent, aren't they? All right angles are congruent. You don't, if you say that they're a right angle, you don't need to say, oh, so their measures are 90, so then they're congruent. All right angles are congruent. Don't forget that theorem. Okay, that'll save you a couple of steps. So that's the perpendicular transversal theorem. In a plane, if a transversal is perpendicular to, I skipped ahead to the next one. This is actually the lines perpendicular to a transversal theorem. If in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. Well, that's a little different than the one we just talked about too. This one says if two lines are cut by a transversal and that transversal is perpendicular to both of them, what do we know about our two lines? They're parallel, aren't they? So I got to back up a little bit here. I'm going ahead. So if I've got two lines, now what do we know about these two lines? How do you know? Yeah, that's usually your indication, isn't it? Although you kind of want to look. It'd be nice if there was some kind of a statement that said line H is parallel to line K, something like that. So we've got them, and then we have this transversal booking along here. So remember, we know the two lines are parallel. We got this transversal, and it's perpendicular to one of them. It's perpendicular to line H. That's all you're given. Is it perpendicular to line K2? Yeah, it has to be. Doesn't it? Yeah, it has to be. Has to be perpendicular line. Let's see. Why does it have to be? Let's see. If that's perpendicular, what type of angle is that? Right angle. And if these two lines are parallel and they're cut by a transversal, what do we know about the corresponding angles? They're congruent. So if that one's a right angle, yeah, there you go. Pretty simple. I think you guys get this easily. The last one says, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So I have these two lines, and they are both perpendicular to line T. They're both perpendicular to line T. Are they parallel to each other? Yeah. Because if these are perpendicular, they're right angles, and we know right angles are congruent, and if the corresponding angles are congruent, then Lines are parallel, aren't they? These are almost postulates, aren't they? I think you guys would all look at them and say, "Oh yeah, we got this," but they're not quite. They are theorems. There's a little more to them. Take a look at it, the bottom of page 150 at example 2 now. Given H is parallel to K, find those two lines. See the red arrow showing you that they're parallel? And J is perpendicular to H. Prove J is perpendicular to K. So there's a little bit to it. They state the given. They say angle 2 is a right angle because that's the definition of perpendicular lines. They form right angles, 4 right angles. They say angle 2 and angle 6 are congruent because of the corresponding angles theorem. If two lines are parallel, if they're cut by a transversal, then the corresponding angles are congruent. They say the measures are equal. That's the definition of congruent angles. Transitive property, measure of angle 2 is 90. Angle 2 and angle 6 are, their measures are equal. Measure of angle 6 has got to be 90. So if it's 90 degrees, got to be perpendicular. So there's a little bit to these proofs, but not a whole lot. Hey, look, a town in Utah in example 3. Nice square grid pattern. I don't know if you can even see the lines up there, but are line S and line T parallel? How do you know? You guys find line Q? Is line Q perpendicular to both S and T? Okay, so they're parallel, aren't they? Okay. And that's the basic idea. Have you guys traveled outside of Utah very much? Driven around cities outside of Utah? I mean, it used to be, well, it still is. You have a stream going along, and some guy builds a mill right here for all the farms to bring their grain into, and then someone builds a store right here because there's a little stream coming down maybe or something like that, and then someone's like, oh, I'll build a bar over here, and then something like this, and everyone traveling comes down the river, and then they kind of come this way, and then maybe come like this, but then there's a big ravine, so then they have to come like that, and then someone else builds a house here along the road and here along the road, and then they kind of connect those two, and it goes off somewhere else, and things just kind of happen. They kind of happen the way they happen, and the roads end up going wherever that people feel are convenient. You just kind of, that's where you ride your horse, that's where you drive your wagon. Pretty soon that's where you drive your car, and that's where the road is. Is that what happened in Utah? What happened in Utah? Whole bunch of people came in all at once, and then they laid the town out. So Huntington, for example, they just laid the town out. Here's Main Street, 4 streets that way, 4 streets that way, 4 streets this way. There's Center Street, 4 streets this way. Nice square mile. How wide are the streets? Yeah, wide enough to turn a semi around in, aren't they? Wide enough to turn a wagon around that has 6 horses hitched up to it. It's pretty wide, isn't it? They're wide. And they're all nice and square, and everybody, the idea was everybody kind of had a house, and then you had enough place to keep your milk cow and your horse there in a stable and stuff like that. And that's the way everything was set up, and they set everything up at once, all at one time, and they laid it all out. So it works out quite a bit different. And it wasn't that long ago that this is the way it was. My dad, in the summer, they lived in a 16 by 16 cabin at the farm up Huntington Canyon. In the wintertime, lived in Huntington at the house here in Huntington. And they had their milk cow and stuff down here. And so, actually it wasn't that long ago that kind of stuff was going on. Think these guys knew anything about perpendicular lines? How long are the blocks? They're pretty long, aren't they? Like 1/8 of a mile? 1/8 of a mile each one? How'd they get all these lines parallel and perpendicular to one another? They surveyed them? But still, what the heck does survey mean? How'd they do that? With geometry. That's right. Do you think they knew all about what we're talking about today? Yeah. Do you think back when they laid out Washington, D.C., and it kind of looks like this, and everything radiates out, all the roads radiate out, and then there's spiral roads? Do you think they knew something about geometry? Yeah. Do you think back in ancient Greece, 2,350 years ago, that they might have known something about geometry when they built the Parthenon? Stairs. When they built this huge building that's about, oh, I don't even know, across right here, I think it's about 150 feet across that. It's so long along the edge here that they actually put a curve to it, so it actually curves up and comes down, because if it were actually straight, the curvature of the earth makes it look curved. So they put a curve into it. I think the curve goes down. They put a curve into it, so when you look at it, it looks straight. But it's not straight, and they knew that. The columns aren't perfect like this. They kind of bulge out about 1/3 of the way down, and then up from about 1/3 of the way up. They taper. There's not a whole lot to it, but there's some. Why do you think they did that? Yeah, it makes them look taller. Even though, and they're tall. They're very, very tall. Okay, but it makes them look taller to have that little bulge to them and go up. So, this guy that wrote this book, Euclidean Geometry, when he wrote this book in 350 BC, did they know all this stuff already? Absolutely. You're not learning anything new. There's nothing in here really that's newer than, there's some things that are newer than when he wrote it, but not a lot. Maybe 5-10% of it. And even that, everybody's known it since maybe 1200, 1300 AD. So nearly 800 years ago. You're not learning anything new. Does that make you feel any better? People been figuring this stuff out. Heck, most people knew this stuff, most of this stuff, for 4,000 years now. So, and a lot of it longer than that. There you go.